Well, our library is growing. We've just been through another atomic test. For a military man, any one of us, the considerations, the problems of atomic warfare are better understood today than ever before. Military participation in Operation Tumbler-Snapper is a matter of record. Experience to be used for military plans of both warfare and future atomic testing. The Nevada Proving Ground is beginning to be an old stomping ground for a lot of us in the services. On Tumbler-Snapper, as on Buster Jangle back in the fall of 1951, headquarters in the forward area is a boom town called Camp Mercury, lying some 20 miles to the south of the test area. This is the place for living, working, and any recreation you are able to squeeze into a very busy schedule. The Armed Forces machine for atomic testing was better oiled than ever before. Every element of that machine ran a good many long, hard hours, hot days, and cold nights to meet a rigid schedule of nuclear detonations. If you've ever been on an atomic test before, either here in Nevada or overseas at Eniwetok, chances are you've made a good many friendships with people you see only once or twice a year. It's a big fraternity, this Order of the Mushroom, and it's growing all the time, as more and more of us from all the services have an opportunity to be a part of this big effort to collect the know-how for atomic warfare. We're still on the ground floor, but the ground floor is getting a little higher on every operation. There's no such thing as a normal working day on an atomic test. The labor pains continue around the clock until the job is done. Because AFSWAP, the Armed Forces Special Weapons Project, is the joint service agency that plans and coordinates all of the military effects tests that are run on an operation of this kind, a special command, a test command, was created. Tumbler-Snapper, as Buster Jangle, was a combination weapons development and military effect test. A total of 8 nuclear weapons were detonated. Most of the military tests were run on the first 4 shots, the tumbler phase of the operation, consisting of 4 daylight airdrops. However, the 4th tumbler shot did play a part in the AEC weapon development program. The snapper phase of the operation comprised the last 4 shots. The weapons themselves were installed in 300-foot towers and fired during the hours of darkness. Snapper was almost exclusively devoted to AEC weapons development. Since comparatively few military tests were conducted on Snapper, let's take a quick look at that phase first, before we get into the heart of our story. At this moment, the installation of a test weapon is being completed in the first zero-tower cab. In the study of new weapons, like those on the Snapper phase, much depends on instrumentation in close proximity to the bomb itself. The internal workings, as well as the external effects of the weapon, are studied and cross-checked in many ways. The events taking place inside the bomb occur with extreme rapidity, in millionths of a second. An instrument located near the bomb in the cab of the tower must be able to work fast enough and capture enough data to accurately analyze the bomb's functioning before being destroyed. The record of the weapon's behavior, recorded in a millionth of a second before it flies to pieces, is sent back down the coaxial cable from detecting instruments in the cab to a recording station several thousand feet away. The weapon is in position and the firing circuits checked out, ready now for firing from a control panel back at the CP. The underlying philosophy behind the entire weapon development program is to realize the maximum kiloton yield from the fissionable material involved. In other words, obtain the highest degree of efficiency. However, equally important is the continuing development of different weapon types to provide complete flexibility in delivery methods and techniques. At the CP, Scientific and military directors wait out the final few hours. Everything is in place. Everything is ready at the Nevada Proving Ground. From now until each hour, the entire test site, all operations, the detonation of an atomic weapon over the Nevada desert, pivots around one focal point, the fortunes of weather. Here in sequence are the 4 Snapper blasts, detonated atop their steel towers on the 7th and 25th of May and the 1st and 5th of June. The weapon ideas being proof-tested on Snapper involve weapons of a smaller physical size that might be carried externally on fighter-type aircraft in tactical air support of ground operations. Every nuclear detonation is followed up by the priority operation of collecting samples of the unburned fissionable material and bomb debris. Atomic cloud sampling with jet aircraft, an idea tried on Buster Jangle for the first time, is standard operating procedure on Tumbler-Snapper. The jets can get the required samples faster and with less personnel exposure. 2 men ride in the sampler aircraft, a pilot to fly the airplane, and a radiological safety man to help him locate and penetrate the hot spots in the cloud where the required samples can be gathered. The planes themselves are radiologically hot, very hot, because the skin of the airplane has collected bomb debris too. The problems of working with high levels of radioactivity are pretty well understood by this time. The safety precautions have been proven and defined in the course of literally dozens of cloud sampling sorties on previous atomic tests. The approach is realistic. The hazards are understood thoroughly. The cloud samples themselves are collected in wingtip sniffers, specially designed tanks suspended from each wing. Inside the sniffers, chemically pure paper filters are installed to latch onto and hold particles of bomb debris the plane encounters in its passes through the cloud. The operations are simple and literally eliminate the possibility of any serious personnel radiological contamination. All post-blast recovery of sample papers, as well as decontamination of the planes, will take place here, at a safe distance from the flight line. The jets will be ready for operation in about 24 hours from now. Once the sample paper from the sniffer is removed, it is placed in a lead coffin for safe transport to Los Alamos and complete radiochemical analysis. Well, that gives you an idea of the Snapper phase of the operation, of military interest in the weapons development program. Those of us in the armed forces ran almost all of our tests on the airdrops, the first 4 shots of the operation, the Tumbler phase. On Tumbler, we had to get the answer to what was perhaps the most important military question with respect to the effects of atomic weapons since the proof test of the first bomb at Alamogordo. Back in about 1948, a series of curves were prepared on blast pressures versus distance for different heights of burst and different yields of bombs. All our offensive and defensive plans incorporating or considering atomic weapons were based on these curves. These curves are wrong. The error is severe according to more complete data collected on later atomic tests. Diagrammatically, an atomic detonation looks like this. 4 effects are produced: light, heat, radiation, and blast or air pressure. Since blast is the primary destruction force of the bomb, let's take a closer look at the blast portion of the event. The bomb is detonated in relatively cold air. The pressure wave produced by the energy released moves faster than the speed of sound in all directions at the same time, in what is known as the incident shock wave. The air is heated by the sudden compression caused by the shock wave. As the incident wave strikes the ground, most of the energy bounces back in a reflected wave. The resultant peak pressure in the reflected wave is about double the pressure in the incident wave, thereby doubling the destructive power of the shock force, or front, moving across the ground. Because the air behind the incident wave is hot, the reflected wave can move faster and gradually compress the base portion of the incident wave into a wall or stem of boosted air pressure called a Mach Y stem. On a graph, the event looks like this. The greatest pressure, of course, is produced at ground zero by the combination of the incident and reflected waves. The pressure gradually drops off as the waves move out from ground zero until the Mach Y develops and increases the pressure again. It was this amplification which extended the area of damage at Hiroshima and Nagasaki. The Mach Y stem worked over every type of structure: masonry, steel frame buildings, reinforced frame buildings. From a military standpoint, the atomic detonations on Japan seemed to be pretty effective. So Hiroshima and Nagasaki became the norm, the basis for curves on blast effects and damage. During Bikini in 1946, damage to ships in the lagoon and equipment on the beach agreed with blast damage curves developed in Japan. Theoretical height of burst curves were developed from effects observed during Hiroshima and Nagasaki, the Able shot at Bikini, and were backed up by high explosive experiments. During Operation Greenhouse at Eniwetok in 1951, men from each of the services got their heads together and dreamed up the most extensive blast study program up to that date. It involved every principal type of structure, many above, some below the ground, in a variety of orientations to the burst. It involved airplanes in the sky, parts of airplane structures on the ground, tanks, and other types of military equipment. The pre-blast estimates of damage were based on composite blast curves developed from studies of Japan and theoretical calculations. Pressures resulting from the tower shots of Greenhouse were less in some cases by a factor of as much as 2/3 than the original predictions. On the bursts of Buster Jangle, even more severe differences showed up between the predicted blast effect estimates and the actual results produced by nuclear weapons. For unknown reasons, nuclear weapons were producing, in some cases, only about 1/3 the blast pressure that we had expected. This raised some very sobering questions in the minds of military planners. We knew the energy was there, but something somewhere along the line was happening to lessen or cushion the full effect of the blast. Where and why are there such discrepancies in our blast curves? Getting the answers was our priority objective on Tumbler. Several things could be happening. For one, the shock-reflecting characteristics of the target itself might be a factor. For another, the thermal radiation might cause the dust on the ground to stir up to such an extent that it cushions the shock wave. It might heat up the ground and the air layer close to the ground to such an extent that it would alter or soften the full effect of the blast or the development of the total potential force of the reflected pressure wave. On the other hand, perhaps there is a completely unknown reason why our estimates of the optimum height of burst for an atomic bomb were wrong. So nuclear weapons were used for the purpose of establishing new blast curves at the Nevada Proving Ground in the spring of 1952. The first weapon will be detonated over Frenchman Flat, site of Operation Ranger in 1951. This is a dry lake bed with moderately stable soil and generally high thermal reflecting characteristics. The blast measurement line stretches 4,000 feet west from ground zero. 50-foot poles were placed every 250 feet along the blast line, with instrumentation running from ground level to the very top, changing the lake bed from its normally flat, deserted appearance to that of an outdoor scientific laboratory, complete with intricate instrumentation of all sizes and purpose. All of this will help determine the blast characteristics produced by a nuclear weapon over this type of target, and to extensively study phenomena occurring in the air layer close to the ground. To aid the many projects in making a more complete evaluation of their results, the Air Weather Service is installing special instruments to record wind direction, speed, air temperature, and relative humidity. This data will help by recording the exact meteorological situation around the test setups at shot time. Another instrument, known as a blast switch, will record the time of arrival of the shock front at ground level, 10 feet and 50 feet. These are installed at stations along the blast line to give us additional information on blast and its behavior as a function of time and distance from zero. The next set of instruments, Wianco gauges, located at 3 elevations on the pole, will measure variations in pressure with time and distance. Gauges on the pole are parallel to the blast line, and at ground level are flush with the earth. The gauge itself incorporates a pressure-sensitive recording element placed behind the hole in a 17-inch baffle. We're trying every angle and every gadget we can to find out what really does happen when an atomic bomb kicks out fiercely at the world around it. To get a picture of blast pressure driving into the ground, we're installing self-recording accelerometers 5 feet below the surface. At this shallow level, we hope to obtain data on movement of the shock wave, both vertical and horizontal through the medium of Earth. Other accelerometers placed to a depth of 50 feet will record the deeper responses. To get still another cross-check on the shock front or blast wave, as its arrival time is clocked by succeeding stations along the blast line, we're utilizing another type of blast measurement instrument called a Bendix gauge, installed at ground level at each of the stations. At 10 feet and ground level, we're installing dust collectors to see, first of all, if the thermal phase does kick up dust, and if so, to determine the size and density of the material that could possibly be a factor in reducing the power of the shock wave, besides absorbing and retaining some of the heat. By establishing air temperature at ground level, at 10 feet and at 50 feet before the burst, during the period of thermal radiation, and during and after the shock wave, we hope to get one check on the effect of this hot air layer on the shock wave. We're using a self-recording temperature measurement device called a thermocouple, which contains a very delicate temperature-sensitive element capable of recording temperatures ranging from normal temperature on the Nevada desert up to 1,000 degrees centigrade and back again to normal in a few fleeting seconds. At some of the closest stations, we're installing other types of air temperature gauges, 2 and 4 feet above the desert floor, to further our studies on air temperature versus time in proximity to 0 point. We're installing another gadget, a sound velocity recorder, to give us still another cross-check measurement of the temperature of the air above the ground at the time of the burst, during the period of thermal radiation, and up to the time of arrival of the blast wave. This is done by measuring changes in the velocity of sound produced and received by the instrument. We hope this will prove to be still another way to determine the interference of the hot air layer close to the ground with the subsequent blast wave. By sundown, the day before the shot, we had our blast line poles fully decorated like a row of weird Christmas trees. The working scaffolds had been pulled down, the cable trenches filled, and the area leveled. Our job is over for the present. All we can do now is wait. What has been feverish activity during past days and weeks suddenly becomes quiet, studied, in a way desolate. This is the last check, the final inspection by Los Alamos and military test directors as they survey the blast line with its complicated array of instrumentation above and below the ground. All is secure. Frenchman Flat stands alone and ready for the first shot of this operation. Shot day, 0 hour minus 10 seconds. The drop plane has released the first weapon of the operation. And as the bomb falls, smoke rockets are fired to form a grid. High-speed cameras record their responses as a measurement of blast pressures above the ground. This bomb is not a test of a new idea, but a weapon with a 1 kiloton yield detonated at an altitude of 800 feet to closely correlate the effects with the low-yield bomb of Buster Baker. Once the dust is settled and the safest routes for re-entry are chosen for us by the RadSafe people, we quickly move back to the blast line stations to recover our instruments and their very hard-to-come-by data as soon as we can. Although radiation levels are high and working time is short, it's perfectly okay for us to go in and pick up our priority data. We're all understandably anxious to get the answers, although this may take weeks or months of study and evaluation before the final determinations are made. With the first shot of the tumbler phase completed, we're taking the rest of the weapons north, some 10 miles across a ridge of mountains into the next valley, Yucca Flat, site of the Buster operation, to try different heights of bursts over a completely different type of target. Stretching to the south, 12,000 feet from ground zero, are the various military effects measurement lines. The blast line here is basically a duplication of the Frenchman Flat blast line. The target is a bullseye 500 feet across. By comparison with the lake bed in Frenchman Flat, the surface in this area is rough and dusty. By comparison with data we got at Frenchman Flat, we hope our instruments here will tell us if the thermal absorption characteristics of a target affect the shock wave. Here we will also get a valuable check on the effect of the height of burst, on the development and effectiveness of the shock wave and Mach Y stem. Tumbler, shot 2, 15 April 1952. The weapon for Tumbler, shot number 2, is the same size as the one detonated over Frenchman Flat. Yield, 1 kiloton. Height of burst, 1,100 feet. This gave us a chance to detonate the same weapon over both a reflecting and non-reflecting target. 22 April 1952. Tumbler, shot 3. Weapon yield, 30 kilotons. Height of burst, 3,500 feet. The same scaled height as shot number 2. These two tests should together provide an excellent check on the normal blast scaling laws. To help the defense establishment produce their new height of burst curves, the Air Force dropped the weapon in a standard ballistics case. Tumbler, shot 4, H minus 1 minute. Yield, 20 kilotons. Height of burst, 1,050 feet. We have had the opportunity to measure and study the characteristics of blast, the basic destructive force released by an atomic bomb, to study it in the course of 4 detonations over 2 types of targets, 3 different heights of bursts, and 3 different yields. The Tumbler operation provided good experimental data on which we can base new height of burst curves for operational use. These curves falling between the old theoretical curves and the data obtained during Buster, providing for the first time experimental proof of the advantage of detonating an atomic bomb high in the air when weak targets such as aircraft are involved. We also found that the normal cube root blast scaling laws developed from high explosive tests apply to the blast pressures from atomic weapons. A new phenomena which may account for the low pressures measured on previous tests was observed for the first time on the 4th shot of Tumbler, a so-called precursor pressure wave moving out from ground zero in advance of the incident shock wave from the bomb. This precursor wave may be caused by the intense thermal radiation released at detonation. We'll have to study, analyze, and cross-check, and then return to our outdoor laboratory again to proof-test our findings. But blast phenomena wasn't the only thing studied on Tumbler. Let's go back and take a look at some of the others. Before Tumbler, there was little information about the effects of blast on aircraft dispersed in the vicinity of the burst. We didn't know for sure how much blast pressure an aircraft could withstand and still take off on a mission. So we moved a variety of aircraft types into stations at various distances from ground zero. The aircraft themselves were positioned in a variety of orientations to the burst. Some faced directly into it, some directly away, some at oblique angles, some at right angles. Will orientation be a factor? If so, how much? Since a fighter is built to withstand greater load factors than a bomber, will the fighter sustain less damage? Will jet planes, which are built to withstand the great pressures of high speeds, sustain less damage than conventional aircraft? We're primarily attempting to define the damage area limits under the different conditions of detonation. So if a plane was not damaged on one shot, we moved it closer for the next shot in an effort to find the breaking point. Some aircraft themselves are instrumented to record the strains and pressures inflicted upon them. We're backing up the instrumentation in the planes with thermal measurement instruments near them on the ground. We have positioned some of the planes behind shields and revetments to help us analyze the value of passive defense for enemy aircraft and for our own planes. We're going to get a lot of valuable information, too, on the effort required to return aircraft to an operational status after exposure to a burst. Shot day. The effects of an atomic bomb on aircraft. After a shot, we're all anxious to get back to our test setups and see for ourselves what happened. The data is here. It only needs to be recovered and analyzed in order to be applied to the plans and problems of atomic warfare. Among many other things, we learned that bombers do receive more damage than fighters. Jet aircraft generally sustain less damage. Planes in a side orientation to the burst receive the greatest damage. In all cases, damage is closely related to the height of burst, distance from ground zero, and kiloton yield of the bomb. Planes in some cases can be returned to operational status after exposure to an atomic detonation. Some can go into operation immediately. Hopefully, this program will give our military planners a great deal of new and vitally important offensive and defensive information. While we're trying all the time to better our position and approach to offensive use of atomic weapons, we're trying just as hard in the other direction to learn all we can about protection and defense against effects of the bomb. Normally in combat, when a man doesn't have something like a trench or a foxhole to seek shelter in, he takes advantage of whatever protection is available, such as a forest or heavy foliage. So we went to Mount Charleston near Las Vegas, selected and carefully removed some evergreen trees that were in perfect condition to bring to the test site. We've been making studies for years on the thermal characteristics in different forest situations. By pulling trees over, breaking them, and various other tests, we have developed some very reliable systems for estimating the static forces necessary to damage trees. Now we need to learn the reaction of trees to the dynamic forces and thermal radiation produced by atomic weapons. Once the trees arrived at the site on special trailers, they were carefully removed to minimize the amount of breakage and planted in concrete foundations at varying distances from ground zero. Since we know the breaking point of these trees pretty well, we're trying to place them in positions and at distances to measure how much the trees will bend under the shock wave forces. Then we know how much more it would take to break them. We're instrumenting the trees with strain gauges, scratch gauges, and other gauges. Some of our other trees are like something right out of science fiction. During the operation, they took on the nickname of lollipops. Actually, they're idealized tree models, consisting of flat metal plates mounted on steel beams. The lollipops are instrumented to help us determine the motion and bending strain on trees subjected to the fierce pressures in the shock wave. This combination of real and idealized model trees will also help us to get a good reading on the drag forces of tree crowns. Fires may be a discouraging factor too. So we're setting out a variety of things that could ignite and burn in a forest. These are known as forest fuels, materials that might carpet the floor of any forest, such as logs, pine needles, beech leaves, cheatgrass, moss, and fir needles. The blast and fire of an atomic bomb are even more dangerous in populated areas. So we're exposing specimens of common structural details, covered and uncovered wall angles, some bare, some exposed with materials that will ignite easily, approximating inflammable trash found in almost any urban area, plus various types of roofing. All of these structural components are without defects that would tend to cause them to ignite or burn. All of this to determine the vulnerability of building components to ignition and sustained burning from atomic weapons. We're also setting up cubicles or miniature buildings to relate the study even more specifically to the problems of a city exposed to an atomic bomb. To find out what ignites inside, we're installing various types of furnishings, such as wood tables and chairs. This project is looking for primary ignitions, not secondary ones from overturned stoves or damaged electrical circuits. We're also going to be able to study the interaction between thermal radiation and the blast wave, and the characteristics of the blast wave in spreading or putting out fires. Our forestry line is ready. Shot day. About shockwave effect on our trees, we learned that they are fairly flexible even against the dynamic force of the bomb. There was a minimum amount of breakage and little damage from flying missiles. However, all of our stations did not come out unscathed. We found that with trees in good condition, generally good thermal protection will be available, thus lowering the degree of burning and the ultimate area of damage. But a full evaluation of their blast protection or hazards will depend on more extensive tests in the future. Our fuel samples were upright to provide the most ideal conditions for igniting and to help us find the limits of the bomb's ability to start and blow out fires. It is only relatively close in that the shock wave blows out a fire. Our miniature buildings and structural specimens gave us valuable data and confirmed many predictions. Sustained burning will not occur if structures in good condition are beyond the primary blast area. After the heat from the bomb has diminished, the fire will generally go out. There would probably be some ignitions through open and broken windows. Then we set out to broaden the foundation of knowledge on which we can reliably base troop participation in atomic warfare. First of all, we want to learn more about the effect of atomic bombs on the combat tools of ground troops. So we're going to let the blast work over a wide range of implements used by soldiers in the field. A cross-section of everything that rolls or shoots will be exposed in a variety of orientations to the bursts and at several distances from the detonation, from large artillery units and heavy machine guns to light weapon emplacements. Shot day, Camp Desert Rock, H-5 hours. Throughout much of recorded military history, it's clear that the effectiveness of troops is geared to their psychological attitude toward the weapons used and situations encountered. At their base camp, Desert Rock, these men are mustering for an atomic warfare maneuver, only the second series of its kind in history. Though they are very much a part of Tumbler-Snapper, they operate independently as they would on a military maneuver. They've all been thoroughly briefed on the hazards, precautions, and techniques of their tactical operations in the area of a nuclear detonation. After the time check, the word is roll out. Every man is accounted for. Every man has his own film badge to record the degree of his own personal exposure. Every group is accompanied by trained radiological safety monitors to be with them in the contaminated areas. Yucca Flat, Desert Rock entrenchment area, 4 miles from ground zero. H-90 minutes. Like all too many people, both in and out of the military, before these men got their assignment for this operation, they had many misconceptions about the bomb and its effects. Some of them thought they would never again be able to have families. Some of them expected to be deaf or blind. Some of them expected to glow for hours after the bomb went off. Like so many people, many of them were afraid. They had never taken the time or invested the effort to learn the facts about what to do in case of atomic warfare. These men have been indoctrinated in what goes on and what to do when the bomb goes off. Any doubts that are left will be eliminated after the full experience of this operation. Planning level observers from throughout the defense establishment have an opportunity to study the maneuvers from close range. H hour minus 5 minutes.
May I have your attention? The B-50 type aircraft you see overhead is the drop plane on its bombing run. The time of fall will be 40 seconds. You will hear the countdown from the bomb away until the burst time. Remain in your holds until the command raise has been given at H plus 3 seconds. If you stand up too soon, the intense light will temporarily blind you, and the heat will give you the equivalent of a severe sunburn. When the command raise has been given, stand up and lean against the rear of your foxhole. This will brace you against the shock wave, which will arrive at this point at burst time plus 25 seconds. It is now H minus 2 minutes. Everyone kneel down in your foxholes, look down, and stay down.
Before the Desert Rock maneuver can proceed, before anybody can go back to his test setups to recover instruments and information, the entire blast area gets a radiological survey a matter of minutes after the shot. The armed forces are responsible for all radiological safety on the operation. This is very important experience for military preparedness as well. The helicopters can hover close to the ground, survey and double-check any questionable areas. Re-entry routes and procedures are determined accordingly by the men of RadSafe Operations and the commanding general of Desert Rock. On 3 of the Tumbler shots, the Strategic Air Command operated bombers at operational altitudes above the burst. This is another part of the Defense Establishment program to give more service people the experience and confidence for atomic warfare operations. We re-enter our display areas close to ground zero once RadSafe okays us for the move up. Since the biggest value of the operation is for us to prove to ourselves that it can be done and find any weak points in the training, psychiatrists are with us to study our reactions before, during, and after the experience. No one can ever fully make you realize what you'll see and feel when you experience an atomic weapon detonated for the first time. It's quite an experience, no matter where you are to watch it. This kind of experience is immensely valuable for any military man, and it will be a part of the tactical training for a great many Army and Marine field forces in the future. In the minds of many of the men, there was doubt and fear before. Now there is confidence. Confidence that comes only with experience. Just treat it with respect rather than fear. Use a little common sense and observe a few basic precautions. After the walkthrough, we moved back out of the contaminated zone to our parking area. We made it, and so can anyone else who goes through this kind of operation. 3 months ago, all the gold in Fort Knox wouldn't have made us want to do it. Now we wouldn't take anything for the experience. We've proved a lot to ourselves and to a lot of other people who need to know it can be done. And we're proud of it.